So when you're asked about the percent yield of a reaction, the percent yield is expressing out of how much you could possibly get as your maximum amount of product, how much of that you actually got. So what you'll do is take the actual yield, okay, or the experimental yield, what you actually physically obtained in a lab or told someone else got in the lab, and you divide it by the theoretical yield, okay, which is the maximum on paper you could get if you use up all the limiting reactant. And to convert that to a percentage, you're just going to times it by 100, okay? So that's all you have to do to get a percent yield, okay? Now, ALEKS is going to be really fun about this, and it will give you your actual yield in the question. So whenever it says, oh, I've made this amount of stuff, you can identify that as your actual yield. So in that case, it's going to be this, right? The actual amount of product you get. But we're going to have to calculate the theoretical yield ourselves, okay? So we've got to do another limiting reactant problem. It's a limiting reactant problem in surprise, okay? So to do that, we have to have a balanced chemical equation to start with. So H2SO4 would be our aqueous sulfuric acid, NaOH would be our sodium hydroxide, and we're going to make sodium sulfate, Na2SO4. Okay, so just always be thinking about ionic compounds and how we write the formula of a salt that's electrically neutral. Sodium is group 1 cation, so sodium plus, the sulfate ion is SO4 2 minus, so we need 2 sodiums to balance that, right? All right, so that's not balanced. I've got 2 sodiums over here, 1 over here, so I've got to do this. Okay, quick bit of bookkeeping. Do I need to do anything else? 1, 2, 3, 4 hydrogens. Yes, I need to do that. Okay, so now we have a balanced chemical equation. So information I'm going to need, I'm asked about water as my product, so I'm going to need the molar mass of water. Okay, so the molar mass of water is 2 times 1.0079 plus 15.9994. Would help if I got all the 9s. So that is going to be 18.012 times 1.0079 plus 15.9994, 18.0152 grams per mole. Right, so we've got the molar mass of water. We're going to need the molar mass of both reactants, so sulfuric acid, so 2 times 1.0079, plus sulfur is like 32.0, I think that says 68. Yeah, 68, and then 4 oxygens, 4 times 15.9994. Okay, 2 times 1.0079 plus 32.068 plus 4 times 15.9994 gives me 98.0802. Hopefully I've done that right. I'm sure somebody will tell me if I did not. Okay, and then we need the molar mass of the sodium hydroxide, NaOH. Sodium is like 22 point something, 22.9897. I think that's all I can read. 22.9897. That will do. That's plenty of sig figs. Plus oxygen 15.994 plus hydrogen 1.0079. 22.9897 plus 15.9994 plus 1.0079 gives me about 39.997 grams per mole. All right, so now we're set up. So what we've got to do is we've got to get our mass of sulfuric acid to our moles of sulfuric acid, and then we're going to use our mole ratio to get from our moles of sulfuric acid to our moles of our product we're asked about, in this case water, from our moles of water to our mass of water. Which reminds me, I didn't write mole ratios from the balanced chemical equation, so I might as well just do that right here. We can see for every 1 mole of sulfuric acid, we make 2 moles of water. So 1 mole of H2SO4 forms 2 moles of water. There you go, 1 mole ratio. I'm just going to stick it right there so you know where we're going to use it. Okay, so mass of sulfuric acid was 5.9 grams. Use the molar mass that we just calculated, 98.0802 grams for every 1 mole of sulfuric acid. Write the moles of what, because we need to know what we're going to cancel out here. We'll use our mole ratio, 1 mole of sulfuric acid. Hello, I need a bigger box. Forms 2 moles of water. And then finally, you want the moles of water to cancel out to give us our mass in grams of water, so 18.0152 grams. So we should be able to see that everything is cancelling. as we expect. So mass in grams cancels, moles of sulfuric acid cancels, moles of water cancels, giving us our mass in grams of water. So 5.9 divided by 98.0802 times 2 times 18.0152. Would help if I could use my calculator. It's got a sticky button. Oh my goodness. 5.9 divided by 98.0802. Having to smash these buttons here times 2 times 18.0152. Really? It's giving me a negative number. I'm going to have to use this phone calculator instead. Grumble, grumble, grumble. 5.9 divided by 98.0802. You guys have already worked this out and are super bored of me. 18.0152 gives me 0.65 grams to two significant figures. But we've got a number. That doesn't mean we've finished. We've got to do the same thing for our other reaction. So our mass of sodium hydroxide, we've got to calculate the moles of sodium hydroxide, and then we can get to the moles of water, and then we can get to the mass in grams of water. Okay, so the mole ratio between sodium hydroxide and water from our balanced chemical equation is 2 to 2. Okay, so that's the same as 1 to 1. So, but we're going to 2 moles of sodium hydroxide equals 2 moles of water. Just stick it in straight from the equation. Okay, so what mass of sodium hydroxide do we actually use? We use 7.3 grams. So convert that mass into moles using the molar mass, which is 39 point, where is it, 997 grams. And then convert moles of sodium hydroxide to moles of water. Okay, so we want the moles of sodium hydroxide on the bottom there, and the moles of water on the top. And then finally, we want to convert moles of water to mass in grams of water. I think I've got an extra 0 in there that's not supposed to be there. Mole of water. Okay, so everything should be cancelling. Okay, always check that your units cancel like what you're expecting. So mass in grams cancels, moles of sodium hydroxide cancels, moles of water cancels. Straight in with the phone calculator this time. Okay, 7.3 divided by 39.997 times 2 over 2 times 18.0152 gives me 3.3 grams. 3.3 grams is definitely more than 0.65 grams. So we can't get that. No. So the theoretical yield must be that 0.65 grams. Once we've made that, all the sulfuric acid is used up and we can't make any more of our water. Okay, so then going back to our percent yield, then it's going to be our actual yield, which was given to us in the question of 1.32 grams divided by our theoretical yield. Hang on, that seems, I've screwed something up here. Let me just check. I found the mistake when I was having a little argument with my calculator. That doesn't come out to 0.65 grams, but it does still come out to be the theoretical yield. It's just 2.2 grams. Does that sound more reasonable to you guys? Yes, it does. Okay, so the actual yield divided by the theoretical yield was actually 2.2 grams, not 0.65 grams. And then we're going to times that by 100 to convert that into a percentage. Okay, so now in the real world, your actual yield may be more than your theoretical yield because you may have an impurity, you may have product that is wet, etc. So, you know, just preparing you for real life, aka lab. So I get 60% for that one. Or going to be real fussy with sig fig 60%. Okay, so that is how I would calculate the theoretical yield. Percent yield. Take your actual, divide by the theoretical, times by 100. So this does hinge on you being able to work out which one of your reactants is the limiting reactant and which mass that you get is the theoretical yield.